So we're talking about trig functions of special angles. I don't know if you guys have a record button, but it's literally like one of those buttons at the bottom that's big like everything else. It's like, oh yeah, it's right there. So the first angle we're going to look at is 45 degrees, also known as pi over 4 radians. And there's a couple ways of doing this, but kind of one of the standard ways is starting with a square, which I know is not a triangle. So we're going to start with a square. Let me get my board a little bit tighter. Of side length 1. And then what we're going to do is we're going to cut the square in half to make a triangle. So we're going to cut it along the diagonal like this. This angle is a right angle, which is 90 degrees or pi over 2 radians. And each of these angles are the same. They're both 45 degrees or pi over 4 radians. Same deal either way. And so then we're going to take this and we're just going to, so I like to redraw it. So we just have the triangle. So here's our triangle with base 1, height 1, angle pi over 4. And before we can find the trig functions of this angle, we need to find the third side of the triangle, right? Whenever we're trying to find the trig functions of an angle and a triangle, we really need to know all 3 sides of the triangle. So we're going to find that third side using the Pythagorean Theorem. I'm going to call this third, you can really call the third side whatever you want to call it, X or Y or C or happy face, right? Really any variable you want to use is fine. X is pretty standard, so I'm going to call that X. And then I'm going to say 1 squared plus 1 squared equals X squared. So 1 squared is 1, 1 plus 1 is 2. So 2 equals X squared. So X equals the square root of 2. I should point out, because this comes up later, right, there's actually 2 solutions to this equation. Right? X squared equals 2 has a positive and a negative solution. Right? Negative square root of 2 is also a solution here. But when we're talking about triangles, we usually think about all the sides having a positive length. So we're going to call that positive root 2. All right, so now I'm going to find the 6 trig functions. So sine of pi over 4 is going to be the opposite of the hypotenuse, which is 1 over the square root of 2. Sometimes it's fine to leave it like that. Often we multiply by root 2 over root 2 to rationalize it and get the square root of 2 over 2. The thing I remember most about the angle pi over 4 is that sine and cosine have the same value. So sine of pi over 4 is root 2 over 2. Cosine of pi over 4 is the adjacent over the hypotenuse, which is also 1 over root 2, which rationalizes as the square root of 2 over 2. So whenever I think about these special angles when it comes to trig functions, I'm always like, oh yeah, pi over 4 is the angle where sine and cosine are the same. And then tangent of pi over 4 is equal to opposite over adjacent, which is 1 over 1, which is just 1. And then for the rest of them, I'm not going to look at my triangle anymore. I'm going to use the reciprocal properties. I'm going to use the fact that cosecant is the reciprocal of sine. So if sine of pi over 4 is 1 over root 2, cosecant of pi over 4 is root 2 over 1, which is just the square root of 2. And secant of pi over 4 is also going to be the square root of 2 because it's the square root of 2 over 1. And cotangent of pi over 4 is going to be the reciprocal of 1, which is just 1. So this is one of the 3 angles that you're really going to want to eventually kind of just memorize what the trig functions are. And you're allowed to kind of remember it however you want. I typically, at least when I first learned this, I really remembered it by remembering what this triangle looked like. So I think it's good, if you don't already know what the trig functions of pi over 4 are, to have this right triangle in your brain. The one where the base and the height are 1, and the hypotenuse is the square root of 2. I will also point out, just because it comes up later on, this is the only right isosceles triangle. So it's a right triangle where the base and the height are, or the two of the sides are the same length. I say it's not the only one, but every other one has the same angles, right? You could have a bigger triangle where the sides are like 500 and 500 and 500 times the square root of 2. It would still essentially be a similar triangle. So that's one of the 3 special angles. Are there questions about this?
Is it fine if you repeat how you got cosecant and secant?
Yes. So whenever I'm finding cosecant, secant, and cotangent for that matter, I'm always using these original trig functions. So whenever I'm finding cosecant, even if I haven't found sine, I'm thinking of it as the reciprocal of sine. So sine was 1 over root 2 before I rationalized it. Cosecant is the reciprocal, which is root 2 over 1, which when you divide by 1, it's just the thing. So I just wrote root 2. The same thing for secant, right? Cosine of pi over 4 was 1 over root 2. Secant is the reciprocal, so secant of pi over 4 is root 2 over 1, which is just 1. And the same is true for cotangent. Tangent of pi over 4 was 1. Tangent of pi over 4 was 1. Cotangent of pi over 4 is the reciprocal, but 1 over 1 is just 1. And that is almost always how I am finding cosecant, secant, and cotangent, is by finding the related trig function and then using the inverse or reciprocal. I should say reciprocal, because inverse sometimes means something else. Okay. And that, we'll definitely see that for the next angles as well. I'm trying to make sure I don't. My board sometimes gets too tight if I turn it the wrong way. I think that was the wrong way. Nope, that's the wrong way. Okay. Sorry. What do we do? So that's one of the 3 angles. Let's look at the other 2. Which one do I have next? I mean, it really doesn't matter. So the next angle I want to look at is, well, let's actually draw the picture first. So the next picture I'm going to draw is an equilateral triangle. Pretty good job. That looks all right. Where each of the side lengths is 2. And of course, all the angles are 60 degrees or pi over 3 radians. So I'm going to say this is 60 degrees. Similarly, I'm going to say this is pi over 3 radians. I'm not going to label this one here because here's where I'm going to cut this triangle in half. I'm going to cut it in half. And then if I cut this angle in half, that's going to be a 30-degree angle, or pi over 6 radians. And I'm going to use one of these half triangles, I should say one of these half of an equilateral triangles to actually find the trig functions of the angle I want. So what I really want is this triangle where the base, where this angle here is pi over 3 or 60 degrees. This angle here is a right angle, so 90 degrees or pi over 2. And this angle up here is pi over 6 or 30 degrees. So you can write it like this, or this is pi over 2. Or if you prefer, you could draw the triangle, the same way, except this is a 60, you could say that's 60 degrees, that's 30 degrees, and that's 90 degrees. More important, my second triangle looks way less good than my first triangle. I'm like, wow, the second one looks kind of sloppy. Oh well. This length, the hypotenuse, is still 2. And the base of each of these, well, I cut this right in half. The base is just 1. But we are going to use the Pythagorean theorem to find the third side. So let's call that third side, let's call it x. Why not? X is my go-to choice. Supposedly, the reason why x is the variable of choice is because when they were typesetting mathematical books back in the days, they had a lot of extra x's around, so that was the letter that they used for variables. I don't know if that's actually true, but it's a story I've heard. So to find x, again, Pythagorean Theorem. So I'm going to have 1 squared plus x squared equal to 2 squared. Just a reminder, it's always the hypotenuse side that goes by itself, and the other two sides, the legs or the base and the height, if you want, that go on together. So solving for x squared, I have 1 plus x squared equals 4. X squared equals 4 minus 1, which is 3. So x equals the positive square root of 3. So this is a triangle that's worth memorizing. It's the 30, 60, 90 triangle, and the sides are 1, root 3, and 2. Or the angles are pi over 6. 30, 60, 90 definitely rolls off the tongue better than the pi over 6, pi over 3, pi over 2 triangle. That's a lot more to say. But those are the angles and those are the sides. And something I always remember about actually any triangle, this is true for any triangle, not just for this triangle, is that the smallest side is always opposite the smallest angle, and the biggest side is always opposite the biggest angle. And the medium side is always opposite the medium angle. So here, smallest side is 1, smallest angle is 30 degrees, or pi over 6. Biggest side is 2, opposite the biggest angle, which is pi over 2, or 90 degrees. And the medium side is the square root of 3, it's about 1.7, and it's opposite the medium angle, which is pi over 3, or 60 degrees. So that's kind of, sometimes people have a hard time remembering how to draw this triangle. And so I always remember, oh, the smallest side goes opposite the smallest angle, and so on. So if I was going to draw it reoriented like this, I would say, okay, well, here's my smallest angle, pi over 6, and here's my smallest side. Here's my biggest angle, pi over 2, and here's my biggest side. And here's my medium angle, pi over 3, opposite my medium side, which is the square root of 3. You don't have to redraw it in different orientation to be able to find the trig functions. Sometimes it's just nice. Come on, eraser. So I was going to set an alarm. Oh well, I'll do that tomorrow. I'm going to remind myself a note. Set an alarm for when class ends. Okay, so I want to find the 6 trig functions of, let's do pi over 6 first. Just 30 degrees. And hopefully you will have noticed this so far. We're always going to write them in the same order for writing all 6. I'm always going to do sine, cosine, and tangent first. And I do also want to emphasize, I haven't seen this on anyone's work yet, because I haven't looked at your work yet, but I've definitely seen this from past students. Whenever you're writing sine, cosine, and tangent, there needs to be an angle, right? It would be incorrect to write that sine was equal to the square root of 3 over 2. Because without the angle there, no one knows what we mean. So we have to say, oh, sine of pi over 6. That's the wrong answer though, right? That would actually be cosine of pi over 6. Sine of pi over 6, so I was actually looking at this angle when I did opposite of hypotenuse. Sine of pi over 6 is the opposite of the hypotenuse, which is 1/2. You could write it as a decimal if you really wanted, but we almost usually always write trig functions as fractions, unless there's a good reason not to. Cosine of pi over 6, again, looking at this angle, or this angle, right, same thing, is the adjacent of the hypotenuse, which is the square root of 3 over 2. Or the adjacent of the hypotenuse, which is the square root of 3 over 2. And tangent of pi over 6 is the opposite over the adjacent, which is 1 over the square root of 3. Which rationalizes, if I multiply by square root of 3 over square root of 3, it's the square root of 3 over 3. So I do those 3 first, and then I find the other 3 by finding the reciprocals. So cosecant of pi over 6 is going to be 2 over 1, which is just 2. Secant of pi over 6 is going to be 2 over root 3, which we should rationalize. If we multiply by root 3 over root 3, we get 2 root 3 over 3. Lastly, cotangent of pi over 6 is equal to the reciprocal of tangent, so it's root 3 over 1, which is just root 3. Sorry, those look like they're a little smushed together. All right. So now let's do the same thing for pi over 3, which is going to look very similar to this, but a little bit different. And I wish I had enough room on this board to write them all on the same side, but my writing is too sloppy or big for that. So I'm going to go to the other side and then we'll go back and forth. So again, don't hesitate to stop me if you have a question. If I am not seeing something you might be typing, just speak up. Let's see. Okay, so that was pi over 6. Now we're going to do the 6 trig functions of pi over 3. And so I'm going to draw the triangle again, even though I just drew it. The orientation doesn't really matter, but I know that most people usually like to draw the triangle so that the angle that they are dealing with is the one kind of in this lower left corner. Like that's just, for me anyway, that feels like the standard way of drawing the triangle. So the angle I want is pi over 3. And this is a right angle, and this is, you don't have to fill in this other angle, but it is pi over 6. And then, okay, I'm gonna ask you guys, what length goes down here? You can type it, you can say it. Volume on. Oh, I'm sorry. Oh, yeah, good. All right, that's excellent. 1. What's the hypotenuse? Yes. And then the other side has to be, that one might be harder to type. The square root of 3. No, we wrote it yet, but I knew you guys were going to get there. So, right, again, smallest side opposite smallest angle, biggest side opposite biggest angle, medium side opposite the medium angle. And so now, sine of pi over 3 is the opposite of hypotenuse, which is the square root of 3 over 2. Cosine of pi over 3 is the adjacent of the hypotenuse, which is 1 over 2. And tangent of pi over 3 is the opposite over adjacent, which is the square root of 3. Similarly, or not similarly, but then cosecant of pi over 3 is going to be the reciprocal here, which is 2 over root 3. And we know that that rationalizes to 2 root 3 over 3. I am not so concerned with rationalization, but some people really are. So I feel like you should practice rationalizing it because a lot of teachers are going to want you to rationalize these things. So we should just get used to doing what people are going to want. Secant of pi over 3 is going to be 2 over 1, which is 2. And cotangent of pi over 3 is going to be the reciprocal of tangent, which is going to be 1 over root 3, which rationalizes as root 3. A couple things to point out. These values are all the same values as the trig functions of pi over 6, just switched around. Right, sine and cosine have the opposite values, right? If we look on the other side, Their sine was pi 6 is 1/2, and cosine of pi over 6 is root 3 over 2. Here, sine of pi over 3 is root 3 over 2, and cosine of pi over 3 is 1/2. So something I remember about these two angles, pi over 3 and pi over 6, or 60 degrees and 30 degrees, is that sine and cosine always take on these two values. One of them is root 3 over 2, and one of them is 1/2. And I just kind of have to figure out which one is which, and then I know the other one automatically. And then the rest of it just kind of fills in. But I also want to say, just like these two switch values, so do secant and cosecant, right? Here, cosecant is 2 and secant is 2 root 3 over 3. And so do tangent and cotangent. Here, tangent is root 3 over 3 and cotangent is root 3. And on the other side, it's vice versa. Tangent is root 3, cotangent is root 3 over 3. And what we're seeing here is a fact of right triangles and really complementary angles. That if you have angles that are complements, meaning that they add up to 90 degrees. So if you have a triangle and one of the angles is a right angle, the other two angles are always going to be complementary because the leftover is 90 and they have to add up to 90 degrees or pi over 2 radians. This kind of thing is always going to happen where complementary angles, sine and cosine, are each other for the complement. And so are tangent and cotangent, so are secant and cosecant. In fact, that's one of the reasons they are named the way they are. Each pair of co-functions, sine and cosine, tangent and cotangent, and secant and cosecant, have the same values for the complementary angles. So let me show you kind of one non-special angle example of this, but I should kind of stop here for a minute. These three angles, pi over 4, pi over 6, and pi over 3, these are the three special angles that most people will expect you to know how to evaluate relatively rapidly and easily. So you should definitely practice finding sine, cosine, tangent of these, which I think I was in some ways not smart because I don't think I asked you to find these on your homework. That said, it's still something you should practice doing because you're going to definitely use these to find sine, cosine, and tangent of other angles. All right, so what time is it? Okay, got 20 minutes. Probably don't need to say the thing about cofunctions, but I'm going to say it anyway. So real quickly, if we have just some random right triangle, where I'm going to call this angle alpha and this angle beta, and I'm going to make up some sides. Let's say this side is, I don't know, 6, 8, and 10. I just took my favorite kind of 3, 4, 5 triangle and doubled each side. It's another Pythagorean triple. So here's what I want you to notice. Alpha and beta are complementary. I don't know why I underlined R. I feel like complementary is the part that should actually be underlined there. Meaning that they add up to 90 degrees or pi over 2 radians. That's fine. What I really want you to see is that the cofunctions of alpha and beta, respectively, are equal to each other. So it is true that cosine of alpha is equal to sine of beta. Cosine of alpha is adjacent over hypotenuse, which is 6 over 10. Sine of beta is opposite over hypotenuse, which is also 6 over 10, which reduces to 3 over 5. Right? And that's true for any of the pairs of cofunctions because of how triangles work, right? For this angle, the adjacent side is the same as for this angle what the opposite side is, and vice versa. For this angle, the adjacent side is the same as what is the opposite side for this angle. So I could also find, say, I don't know, tangent of beta is the opposite over adjacent, which is 6 over 8. And that should be equal to which trig function of alpha? Anybody? Anybody? Volunteer? A brave person?
Cotangent of.
Exactly, yes. And you can either see that by knowing that cotangent is adjacent over opposite. So cotangent of alpha is the adjacent over the opposite, which is 6/8. Or you can see it by knowing that cotangent is the cofunction of tangent. So it's always cofunctions that have this property. Cofunctions of complementary angles are always equal to each other. So one more, I could say that, say, secant of alpha. I don't know what secant is. I never remember secant. I know that secant is the reciprocal of cosine. So cosine of alpha is 6/10, which is 3/5. So secant of alpha is 5/3. And that should be the same as, what's the cofunction of secant? You guys see a lot of my open mouth. I'm waiting.
Cosine?
What was it again?
Cosine?
Not cosine. Cosine is the cofunction of sine. The cofunction of secant also has the name secant in it.
Cosecant.
Exactly. Cosecant. Cosecant of beta. Because cosecant of beta, again, I don't really remember cosecant very well. I know that sine of beta is the opposite over the hypotenuse, which is 6/10, which is 3/5. So I know that the cosecant of beta is the reciprocal, which is 5/3. This might not come up a ton, but it does come up on occasion. So I felt like I should mention it. Getting this lovely black, weird marker dust everywhere. It's really gross. Also, I got pen all over my finger today. It was not fun. Happens sometimes. It's the perils of being a teacher, writing things down. I know it's very perilous. Okay, so now that we have found the 6 trig functions of the special angles, we're going to kind of extend that idea to larger angles that still essentially are the special angles. So I got lots of time. So I'm going to find now the 6 trigonometric functions of what angle have I chosen here? 3π/4, which is equal to 135 degrees. So 3π/4 is in the second quadrant. It looks kind of like this. And what I really care about is this angle here. So that angle there is, well, how much more do I need to get halfway around the circle? Well, halfway around the circle is what angle? Yeah, 180 degrees, or in radians, pi, which I guess for pi, we'll just have to type pi, right? So you can type, I don't think there's a nice way of making pi other than just saying pi. So from 3π/4, or 3/4 of pi, to 1 whole pi, sounds like we're talking about pi, which we are. There's π/4 that's left. And that's one of our special angles. So what I'm going to do is I'm going to drop a perpendicular always to the x-axis. And I'm going to imagine this being my special triangle, where π/4 is the angle. So in this special triangle, the hypotenuse is the square root of 2. And the sides are each 1. Now, this is one of the few times where I'm going to use negative values for my lengths. Almost always, I like to think about a triangle having positive values. But here we're going to pretend like the axes matter. So I know that, let's use green. I know that over here, x is positive, and over here, x is negative. In a similar way, up here, y is positive, down here, y is negative. So for this triangle I've drawn, this length here, I've kind of gone in the negative x direction. So I'm going to say that this base, or this leg of the triangle, which is kind of the x side of the triangle, is going to have a length of -1, which is fine. I don't love it, but we need it for the moment. In a similar way, I'm going to say this height of the triangle is +1. Please stop me if you have questions. So what we're going to do now is we're going to use this triangle, which is essentially the triangle that we used before, to find the trig functions of 3 pi over 4. So it is correct to say, so I think I'm referring, that sine of 3 pi over 4 is equal to +1 over √2, which rationalizes as √2 over 2. And just like sine and cosine before, sine and cosine here are essentially the same. So I'm going to say that cosine of 3 pi over 4 is almost the same. Instead of 1 over √2, it's going to be adjacent over hypotenuse, which is -1 over √2, which is going to rationalize to -√2 over 2. Tangent of 3 pi over 4 is going to be the opposite over adjacent, which is going to be 1 over -1, which is -1. And then the other three feel like I'm going to run out of room. I'll run them anyway. Cosecant of 3 pi over 4 is going to be √2 over 1, which is just √2. Secant of 3 pi over 4 is going to be the reciprocal of this. So instead of being -√2 over 2, it's going to be -2 over √2, or -√2. And finally, cotangent of 3 pi over 4 is going to be the reciprocal of -1, which is still -1. Right? 1 divided by -1 is still -1. So a couple things to be aware of here. Each of the reciprocals has the same sign. Sine is negative, sine is positive, cosecant is positive. Cosine is negative, secant is negative. Tangent is negative, cotangent is also negative. That's always going to be true. Reciprocal functions always have the same sign as the original function. All right. How much? Yeah, I think we can get. So let's look at a few more examples. I'm going to maybe come back to that one in a second. So let's look at I can be smart about this. Yeah. So let's do the same sort of thing for the trig functions of 4 pi over 3. And, well, yeah. So 4 pi over 3 ends up being in the third quadrant because that's 1 whole pi, but 4 pi over 3, or 4/3 of pi, is another third of pi. So 1 whole pi and then another third of the way towards the next pi puts us about right there, and there-ish. I should make that look a little bit bigger. Sorry. So obviously there's really good pictures elsewhere on the internet in case you want other good pictures. So this angle is 4 pi over 3. And again, if this is pi here, then if I drop a perpendicular to the x-axis, always to the x-axis. This leftover angle here, which is called a reference angle, which we'll talk more about on class tomorrow. This angle is pi over 3. And so we can draw the triangle for pi over 3, right? We know that pi over 3 is the medium side. It goes opposite the medium length. We know the hypotenuse is the largest side, which is 2. And we know this last side over here is 1. And this other angle would be pi over 6 if we care, but we don't. Now my picture isn't exactly right because I've gone in the negative x direction and the negative y direction. This should actually be a negative 1. This should actually be a negative square root of 3. So now we can find the trig functions of 4 pi over 3. So sine of 4 pi over 3 is going to be the opposite, which is negative root 3 over the hypotenuse, which is 2. I should point out, in case you're curious, the hypotenuse we always think of as being positive, even if we're going, right, we're kind of thinking of it, it's the distance you've gone from the origin, whereas these have a direction or a negative or a positive depending on where they end up at. And it's really just to make things work. Cosine of 4 pi over 3 is going to be the adjacent over the hypotenuse, which is negative 1 over 2. And tangent of 4 pi over 3 is going to be the opposite over adjacent, which is negative root 3 over negative 1, which ends up being positive root 3. And then we find the other 3 the usual way with reciprocals. Cosecant of 4 pi over 3 is going to be the reciprocal of this, which will be negative 2 root 3 over 3 after I rationalize it. The reciprocal of negative 1/2, so secant of 4 pi over 3 will be negative 2. And cotangent of 4 pi over 3 will be the reciprocal of root 3, which is 1 over root 3, or we rationalize it and get root 3 over 3. All right, so there's a couple of them in the notes that I'm skipping over just to make sure we get to everything. Well, not everything, but to make sure we hit all the important parts. Here's what I want to say about this. This is a perfectly fine way of doing it, but it's time consuming. So there's kind of a faster way after we know how things work. So yeah, let's look at the trig functions of 11 pi over 6. That's almost 2 whole pi, right? We're 1 pi over 6 away from 12 pi over 6, which is equal to 2 pi. So we're all the way in the 4th quadrant. Again, if I drop a perpendicular to the x-axis, this leftover or reference angle is pi over 6. Again, we're seeing one of our special angles from our special triangles. This is pi over 6. This side over here is 1. The hypotenuse is 2. And this side here, the medium side, is root 3. Except really that's a negative 1. And so in this case, I might just do the first 3. Sine of 11 pi over 6 is negative 1 over 2. Cosine of 11 pi over 6 is adjacent root 3 over 2. And tangent of 11 pi over 6 is opposite over adjacent, which is negative 1 over root 3, which is negative root 3 over 3. And I'm going to skip the other 3 on this one just because I think we've seen the other. I think you guys can all find them yourselves, really. You can find cosecant and secant and cotangent. What I want you to observe from these last 3 examples is that So in the first example, which I don't have anymore, when we were in quadrant 2, when the angle was 3 pi over 4, that sine was positive, and the other two primary trig functions, cosine and tangent, were negative. In this example, where the angle was in quadrant 3, tangent was positive, and the other two primary trig functions, sine and cosine, were negative. And lastly, when the angle is in quadrant 4, cosine is positive, and sine and tangent are both negative. And that really has to do with just the orientation, right? Because if you're in this quadrant, this side, which will be the adjacent side, is always going to be positive, and this side, which will be the opposite side, is always going to be negative. So, of course, cosine is going to be positive because the adjacent over the hypotenuse will be a positive over a positive. And of course, sine is going to be negative because the opposite over the hypotenuse is going to be a negative over a positive. So this kind of leads to a useful mnemonic device, which I imagine many of you might have heard before, or different versions before. So the mnemonic device is, so here's Q1, quadrant 1, Q2, Q3, and Q4. And the mnemonic device is that all students take calculus. Well, I should say, that's the PG version of the mnemonic device. There are other versions that I've heard which are a little saucier. I will not repeat those right here. You can Google those yourself, or not, whatever you like. But what this means is here all the trig functions are positive. So sine of theta is positive, cosine of theta is positive, tangent of theta is positive. It's usually pretty standard to only write the first primary three because we know that whatever sine has, so does cosecant. And whatever sine cosine has, so does secant. And whatever sine tangent has, so does cotangent. So when I write these three, I expect everybody to be like, oh, okay. Then I also know cosecant, secant, and cotangent have the same positive signs. Here in quadrant 2, sine is positive, and the other two are negative. So cosine theta is negative, tangent of theta is negative. Here in quadrant 3, the t is what we focus on, so tangent is positive, and the other two are negative. So sine of theta is negative, cosine of theta is negative. And here in quadrant 4, cosine is the positive one, and the other two are negative. And I just want to point out, in quadrant 4, cosecant would also be negative because sine is negative. So what we end up doing is we end up using this information to help us, along with these special angles, find the trig functions of some, well, let me give you an example. And let me use one of the examples I have already to go. So let's say I wanted to find the trig functions of 5 pi over 3, which is 300 degrees. So here's how I would do that. And we're definitely going to do a lot more of this tomorrow. Is I would say, okay, well, 5 pi over 3, that's in quadrant 4. And definitely tomorrow we will also talk about a fast way to identify what quadrant one of these kind of special angles is in. Or really, this is an angle that has one of our special angles as a reference angle. So 5 pi over 3, right about there. I don't really need to draw this picture, but I'm going to anyway. And you won't need to eventually either. The angle that I measure to the x-axis, always to the x-axis. I'm going to say that like every time because it's always true, always to the x-axis, is pi over 3, right? If this angle is 5 pi over 3, we need one more pi over 3 to get us to 6 pi over 3, which is 2 pi. So the angle I'm using, or the special triangle I'm using, is the special triangle that has pi over 3 as the angle. And I know that sine of pi over 3 is root 3 over 2. And cosine of pi over 3 is 1/2. And tangent of pi over 3 is root 3. And so then I can use this knowledge combined with the quadrant, right? I'm in quadrant 4, to say that, well, I have all the values. I just need to change the plus or minusness. And I know we're at the end, so let me just write this. I know that sine of 5 pi over 3, well, since I'm in quadrant 4, it's going to be negative. So it's going to be negative square root of 3 over 2. And cosine of 5 pi over 3, in quadrant 4, cosine is positive, so it's going to be positive 1/2. You don't need to write the positive here, but I kind of like you to emphasize that I know that it's positive versus knowing that it's negative. And finally, tangent of 5 pi over 3 would be negative because we're in quadrant 4, so it's going to be negative root 3. And then I would find the other 3 by doing the reciprocals. So I'm going to erase this here. Cosecant of 5 pi over 3 would be negative 2 root 3 over 3. Secant of 5 pi over 3 would be positive 2. And cotangent of 5 pi over 3 would be negative 1 over root 3, which is negative root 3 over 3. So we can use the special triangles combined with the quadrant we're in to determine what the values are for angles like 5 pi over 3 or 7 pi over 4 or anything where the reference angle, which is the angle you get when you measure to the x-axis, would be a special angle. All right, I'm 2 minutes too far. Again, 2:22, I should stop now.